Since time immemorial, people have used devices to help them calculate. Even a stick can help keep count if you add notches to it. It's a helpful device, but only capable of carrying out one instruction. Just add 1. Over time, devices became more and more sophisticated and quite impressive. Devices helped in doing arithmetic, in navigation, in predicting tide levels, and much more. Then came Charles Babbage in 1833, who had invented a machine that aided in calculating many useful quantities for astronomy. It struck him that his machine could be modified to do more than the operations he had given it, and so he came up with the analytical engine. This engine had instruction cards that would tell it what operation to do. These instruction cards could even tell it to go back to previous instruction cards, or to choose which card to go to based on the state of the machine. This allowed for very sophisticated behaviors. The significance of such a versatile machine was not lost on people. The Countess of Lovelace, Ada Lovelace, was fascinated by this machine. She saw in it a machine that even Charles Babbage failed to see. Babbage saw a machine that could be programmed to do a quite powerful sequence of arithmetic operations. Lovelace saw a machine that wasn't just limited to operating on numbers, but one that could operate on text or music or symbols, since they all have patterns and ways in which they can change, what mathematicians call an algebra. What Lovelace saw was computation. All this hubbub arose from the power of the instructions that the machine could do, despite them being quite simple instructions. So it's natural to ask whether there is a machine that can do even more. The notion of computation was made mathematical over a century later by Alan Turing. It is a very reasonable notion, very capable, and matches our intuitive notion of computation. And it's actually quite similar to the oversimplified analytical engine that we showed. Turing machines also perform very simple instructions, simple enough that even the analytical engine could carry them out. That means that whatever a Turing machine can do, the analytical engine can do too. This probably doesn't sound like a very big deal yet, but this whole video is about where this kind of thinking leads. Because despite sounding very innocent, machines doing what other machines can do puts us in a bit of a bind. Alan Turing created the notion of Turing machines. Each Turing machine has a specific behavior. They could be calculating primes, or Fibonacci numbers, or just giving you your favorite lyrics. Yet as he showed in his 1936 paper, where he described these machines, some of these machines are universal. That means that they can simulate the behavior of any other Turing machine. That sounds weird, but how weird is it? It actually isn't weird at all. You're using something similar right now. Here's an example of some code. This code has a behavior. It starts with some values for each variable, and the code runs and the variables change in a manner determined by the code. But your machine can run the code too. When it runs the code, your machine creates the starting state and simulates each step of the code. So whatever the code can do, your machine can do too. And this is true of any code. Your machine can simulate the behavior of any code. Your machine is a code simulator. But this code simulator is also made out of code. It's just your operating system working as designed. Since it can simulate any code, in particular, your code simulator can simulate itself. If that sounds amusing, it's because it is amusing. Now let's also see some fun consequences of this. Here's the structure of a program that keeps on generating texts until it has generated all texts of length at most 10 to the power 100. The actual code isn't as important as what it does, so you can ignore the code if you want. In the first 200 loops, it will generate all one-letter texts, and then will go on to longer texts. Some of these texts will be gibberish. Some will make sense, and some will actually be valid code. Let's call this whole code the text generator. The fun starts when we use our code simulator on the generated texts. Some of the texts won't be valid code, And our simulator will let us know that. Some of the texts will be valid code, and the simulator will then simulate that code. So this one code above should show a lot of different behaviors. It should show the behavior of every single code of length at most 10 to the 100. Now let's exploit this with some simple modifications to create a humongous number. As we go through each code, let's keep track of what they output and see what the largest number is that the codes output. Now our whole program will output a number larger than that. So the output of this program is huge. It's larger than the output of any program whose length is at most 10 to the 100 characters. But what's the length of the above code? We saw that the text generator is a very small code. The code simulator might be a few million characters long, but not more than that. So our program above is also a small program, being way less than 10 to the 100 characters long. So the output of the above program should be larger than the output of the above program. Oh wait, no. This is what they warned me about. They told me, hey, fine design, you can make a YouTube channel if you want, but just make sure you don't break maths. And I've gone and done exactly that. I've broken maths. I came up with a number larger than itself. Bad fine design. Bad. Well, not that bad actually. We do this on purpose quite often. We make an assumption and then we break maths. We always believe that maths shouldn't be breakable, and so we conclude that our assumption was wrong. We didn't explicitly assume anything in our previous argument, but implicitly we assumed a lot. For one, I didn't really prove that there is a code simulator that's less than 10 to the 100 characters, but that actually works out. The problematic assumption was that the above code goes through all the texts doing what we thought it would. The problem arises when we get a code whose behavior is to run forever. Then our code simulator will also run forever. And so our program will never get the output from the code simulator, and our program will not output anything. Worst program ever. But what if we could write a new code apart from text generator and code simulator? A code that we will call bad code checker. It checks if the generated code will run forever. Then we can make sure that we give code simulator only code that doesn't run forever. That would fix our bad assumption. The problem is that this is really hard to do. Here's a really short and simple code, and if you can tell whether this code will run forever, you'll be hailed as a hero by the mathematics community forevermore. But just because we can't seem to do it, doesn't mean that this bad code checker can't exist. However, what we do know is that if this bad code checker exists and is also well under 10 to the 100 characters, then we've broken maths again for the same reason. This code will output a number larger than this code should output. So our assumption must be wrong, and there cannot be a bad code checker that is smaller than 10 to the 100 characters. By changing the number 10 to the 100 above, we can actually conclude that such a bad code checker program can't exist at all. So wait, if we haven't broken maths at all, then is this just clickbait? Have I stooped so low already? Well, not yet. There is actually a little bit of maths breaking that we will do. In fact, we will be targeting the very foundation of mathematics, proofs. Let's think about what proofs should be like. For one, you should be able to write down proofs. So every proof should just be some text. There should also be a mechanical way of checking a proof. That is, there should be a code proof checker that checks whether a proof is correct. When this code says a proof is correct, it should be the case that the conclusion of the proof is true. This also means that the proof checker code should not run forever, because then you'll never know whether the proof is correct or not, and you'll just be waiting forever, hoping to find out. That's all that we want from our proofs. We now start with a new attempt to write the bad code checker program. We know it can't exist, but let's try this anyway. It gets as input some code, let's call it C. The first thing it does is to consider the statement C will run forever. Although I've written it in English, it actually is a properly rigorous mathematical statement. It is either a true statement or a false statement. If it is a true statement, we want the bad code checker to say that the code is bad. If it is a false statement, it should say that the code is fine. Now we use our text generator again to just keep generating text with no limit on its size. This loop will run forever unless we stop it. For every generated text, we pass it through the proof checker. If it is a correct proof and the conclusion is that the statement is true, then the bad code checker can stop and conclude that the code is bad. If it is a correct proof and the conclusion is that the statement is false, then the bad code checker can stop again, this time concluding that the code is fine. If the conclusion is not related to the statement at all, we move on to the next text from the text generator. So if the statement is true, well, there should be a proof that it's true. At some point, the text generator will reach that proof. The proof checker will certify it, and our code will say that C runs forever. If the statement is false, well, there should be a proof that it's false. Again, the text generator should reach that proof at some point, and then our code will say that C won't run forever. So this code here should actually work. We've created a bad code checker. But that shouldn't be possible, because then, as we saw, you'll end up with a number larger than itself. So where did we go wrong here? Again, we made an assumption. If we go through this argument carefully, we see one possibility that we have overlooked. What if the statement is true, but there's no proof of it? Then this program we've created will keep searching for a proof that doesn't exist. It will run forever. But can that be the case? That something is true but it can't be proven? How do we know it's true if it can't be proven? A true statement that can't be proven is very unsettling. Unfortunately, it's the only way out for us. If we don't want maths to break, we have to accept that there are statements that are true but which can't be proven. If every true statement had a proof, then as we've shown, maths breaks. This conclusion was devastating to many mathematicians who hoped to come up with an all-powerful proof system. I too am disappointed by the dashing of those dreams. But on the other hand, this is a fascinating insight into the nature of mathematics and logic. And similar reasoning gives us many delightful statements. There's Chaitin's incompleteness theorem. It says that despite most numbers being complicated, no numbers are provably complicated. There's Richard's paradox, which says that if you want a powerful way to refer to numbers, then it's impossible to mathematically distinguish between statements that refer to numbers and statements that don't. Look it up, it's fun. But what about people who are trying to prove things? How tough is this result to them? Well, many people don't care about statements like code C will run forever. And there are fields of mathematics where every true statement in that field can actually be proven. For instance, every true statement in Euclidean geometry does actually have a proof. Even for people who do care about codes running forever, this result shows how nuanced the topic is and opens up new avenues to explore. This result about proof systems not being able to prove every true statement was actually shown 5 years before Turing showed off his machines. It's known as Gödel's incompleteness theorem. There ought to be many sources out there that give other angles of looking at it. It's always fun to look at such things from multiple angles. What our bad code checker tried to do is referred to as the halting problem, if you want to look into it a bit more. The fact that the halting problem can't be solved was shown independently by Alan Turing and Alonzo Church. Anyway, that's all for now. See you again when we revisit this topic in part 4 of the BIGNUM Bake-Off series.